In the previous section, we took a look at an example of being able to do a proof that involved a ceiling, or excuse me, a floor function. In this example, we're going to take a look at being able to work with the ceiling function. And so let's say for some reason that we have that for all x and r, and we're also going to say that m is an integer. So let me add that in really quickly, that m is an integer in this case, that the ceiling of x plus any integer is equal to the ceiling of x plus that integer. Again, we're going to have to go back and we're going to have to recall this definition of ceiling. So we are going to use this, and that means that we have to define a real number x, an integer n, and an integer m when we do this. All right, so let's start this. So for our proof, let's let x be an element of the real numbers. Let's let n and m be elements of the integers. And we're going to say such that x, comma, m, comma, n are arbitrary but particular. And you probably remember from last video that we used the definition of the floor. This time we're going to use the definition of ceiling. So we're going to say by definition of ceiling, we're going to say that the ceiling of, excuse me, we're going to say that if n is equal to the ceiling of x, this implies that n minus 1 is less than x, which is less than or equal to n. And we do have to define n as the ceiling of x. Okay, so up here, right before the by definition, we should say let n be equal to the ceiling of x. All right. Now we can use the definition of ceiling. So let me erase this just so that we can kind of put it, or at least move it, so it's in a correct order. All right, I'm just going to move this up just so that way it looks like the right ordering that we want to do. And we'll just move this guy up here. All right, there we go. All right. And so we could go ahead and use that algebra trick. And remember last time that we subtracted 5? Well, now we're just going to add m to everything. Okay, so we're going to say by algebra, we can say that this is going to be equal to n plus m minus 1 less than x plus m less than or equal to n plus m. And remember, we're dealing with a ceiling. So that means that the ceiling of x plus m is really going to be equal to n plus n, right? Because remember, n is the next integer up. So we can say, by definition of ceiling, we can say that the ceiling of x plus m is going to be equal to n plus m. And then finally, by substitution, because remember last time what we did was we substituted, we said that since n is equal to the ceiling of x, we can just substitute that right here, and we would get the ceiling of x, and everything else would be the same. So this would be the ceiling of x plus m is equal to ceiling of x plus m. And that's exactly what we wanted to prove. We wanted to prove that the ceiling of x plus m is equal to the ceiling of x, and then plus m on the outside of the ceiling. Okay, so we can say by above, for all x in the real numbers and n and m in the integers, that the ceiling of x plus m is equal to the ceiling of x plus m. Right. So those are two pretty classic proofs involving the ceiling and the floor functions. Now, one more example And this one's more specific, that we have a ceiling function equal to a statement as opposed to another ceiling function. So we're going to say for all n in the odd integers, which helps out a lot, the ceiling of n squared over 4 is equal to the ceiling of n, I'm sorry, is equal to n squared plus 3 over 4. All right, so let's start out by defining n to be an odd integer. So let's let n be an element of z odd, and we're going to say n is arbitrary but particular. And of course, we know by definition of odd, we can say that n is going to be equal to, let's just say 2p plus 1, where p is an integer. All right. Now we're going to substitute into the equality, and we're hopefully going to simplify this. All right. So let's just go ahead and we're going to say by substitution, we're going to say that the ceiling of 2p plus 1 square over 4 is going to be equal to 2p plus 1 square plus 3 over 4. Right? And now we're just going to algebraically simplify both sides. Right? So we're going to FOIL out 2p plus 1. Right? So remember, this is a FOIL. Okay, so it's 2p plus 1 times 2p plus 1. And that's going to work out to be 4p squared plus 4p plus 1. And same thing on the right-hand side, that's going to be 4p squared plus 4p plus 1 plus 3. Okay, and our justification for that is just by multiplication. Okay, clearly we can do some computation on the right-hand side. So by computation, left-hand side still going to be the same, 4p squared plus 4p plus 1 over 4. And 4p squared plus 4p plus 4 over 4. All right. Now, because we're dividing by a monomial, we can split this up and each of the different fractions, and we can create 3 separate fractions on each side. So we can say by algebra, this is going to become the ceiling of 4p squared over 4 plus 4p over 4 plus 1 4 is going to be equal to 4p squared over 4 plus 4p over 4 plus 4 over 4. And clearly by division, we can yield ceiling of p squared plus p plus a fourth, which is going to be equal to p squared. So notice all we're doing is we're just canceling out the fours, plus p plus 1. All right. Now, think about this for a moment. P is an integer. So that means you have an integer plus a quarter. So wouldn't that mean, let's say that right here is p squared plus p plus a quarter, right, on the number line. Wouldn't that mean that the next integer up from this, in other words, the ceiling, would be p squared plus p plus a quarter, which is the ceiling, which would really be p squared plus p plus 1. Since p is an integer, we really don't have anywhere to go up. It would be integer plus a quarter, so it would just be the next integer up, which would be p squared plus p plus 1. And so by the very definition of ceiling, we would say that this is going to be equal to p squared plus p plus 1, which is equal to p squared plus p plus 1 by definition of ceiling. Right. And clearly these two sides are equal, right? And we verified what it is that we've been asked to prove. So we can say, hence, by above, for all n in z odd, the ceiling of n square plus 1, I believe, if we go all the way back up, it was just n squared over 4, excuse me. So n squared over 4 is going to be equal to n squared plus 3 over 4. All right, so pretty easy proof once you go through and do the substitution. The only difficult part is just noting that you use the definition of ceiling to go from this second to last step to this step right here. All right, so we're all done with floor and ceiling, and then the last topic in this section is going to be indirect proof, proof by contradiction, and proof by contraposition.